Hello, I'm Julien Petry, and I'm a chemical engineer for Softseed, and I've been working on the Pulp&Fuel project with Robert Santa, who is project leader with a knitting engineer background. So we work on the work package 3, which is called process design. And so our role was to work on the upscaling of the process. Basically, we've communicated with the research team and equipment supplier to gather all the available information to design a working plant on a half industrial scale. Using this data, we estimated the cost of every equipment required for the plant to reach the desired specifications, and we also work on the process optimization to make the plant as competitive as possible by lowering the number of units as well as the operational costs. So the process optimization was our first task, and it had the biggest impact on the plant core units. That's why it was our first task. And so the to reduce the CapEx, which is the capital expenditures, and the OpEx, which is the operational expenditures. That would make the plant as viable as possible. The original design included a lot of purification steps and two very different branches for the black liquor and the bark gasifications. In particular, the gasified black liquor branch contained a lot of purification processes to obtain pure hydrogen from this, but we noticed that the yield was too low compared to how many purification steps we had, as we only managed to recover 5.7 kilogram per hour hydrogen using 1 ton per hour black liquor. Therefore, we decided not to purify hydrogen from the black liquor gasification, and we rather make the synthesized gas to the bar gasification products. This allowed us not only to remove some gas treatment steps that were redundant between the black liquor and the bar gasifications, but also to greatly simplify the plant. With other adjustments, we managed to lower the number of units to 10 from 15. After the optimization was done, we simulated the whole plant using the software named Aspenizes, which is a chemical engineering software handling process and utility streams, as well as the different equipment such as reactors, pumps, compressor, or heat exchangers. Using this, we were able to simulate the impact of every single equipment on the process stream conditions, determine the energy required for the different compressors and pumps found in the unit, determine the cooling water flow rates required in the heat exchangers, and so on. And finally, these data were used as a basis to determine the size of every single equipment, and we were then able to give a global cost estimate for the plants. With this, I redo this sentence. Finally, these data were used as a basis to determine the size of every single equipment, and we were then able to give a global cost estimate for the plants. So with this first design, we highlighted several issues. The first one being that the global yield is quite low, as we managed to recover about 200 kilogram per hours hydrocarbons, while we had 1 ton per hour black liquor and 1 ton per hour dried barks as inputs. So this is only 10% yield. The distillation columns to separate the different syncrude cuts had to be very high to have an efficient separation. So we had about a column that was about 40 meters high, while the column diameter only had to be 0.2 meters, which is constructible, but definitely not optimal. So we decided that the syncrude should be directly transported to an already existing crude distillation plant, handling much bigger flow rates so they could mix this syncrude to their normal crudes. A carbon capture unit should have been implemented before the Fischer-Tropsch reactor, However, undesirable molecules would be driven through the reactor, such as ammonia, which would greatly harm its reactivity. So we decided to put this unit in a recycle loop instead after the Fischer-Tropsch reactor, heading back to the Barks gasifier to break or capture the unwanted molecules resulting from this treatment. We've also investigated the possibility to replace this unit with a membrane separation, which will simplify the recycle loop even more and the plant as well. The black liquor gasification has a low yield, even though it requires a reactor that can handle high pressure, high temperature, and salt corrosion. So due to the conditions required for the gasification to take place, we worked with Andrea from Top Industry to design a reactor that could handle these particular operating conditions.
The requirement given by the CEA for the design of the reactor were that it should be able to treat 100 kg per hour of black liquor, which has a pH around 13, work at 700 degrees and 280 bar, which are really critical conditions which subject the equipment to high mechanical strength, and allow a residence time between 2 and 6 minutes to allow the reaction to take place. So in order to fix the volume of an equipment, the inner diameter and its height are the main parameters to work on. The inner diameter is the most important as it has a direct impact on the wall thickness. So it has a direct impact on the amount of alloy which is laid, the final weight of the reactor, so of course on its final price. As for all equipment or units working at high pressure and temperature, the design of the reactor must be made according to DESP standards. DESP stands for Directive des équipements sous pression, which is the European directive for high pressure equipments. Given for this project the high pH of black liquor, the high corrosive supercritical environment and the real critical temperature and pressure, the unique choice we had regarding the alloy was the Inconel 617. In order to respect the requirement of versatility for the residence time, a vertical reactor constituted by 3 modules which can be removed has been designed. The final dimension are 3 meters of height, 125 millimeters of inner diameter, and a wall thickness of 135 millimeters. The problem we met is that at the temperature and pressure required for the process, the mechanical properties of the only one alloy we can use undergoes a critical degradation. They become time dependent and it is not acceptable from an industrial point of view. So at this point we reached the equipment limits and it must be taken into account for the development of this process. Thanks to the fruitful exchanges with the CEA team, the path of study which rose were to focus the attention on the pretreatment of the black liquor, to be able to gasify it at temperature lower than 600 degrees.
Considering all these issues, we decided to make some changes to the global process. Due to the complexity and the low impact of the current black liquor gasification process compared to the whole plant, we decided to separate the non-mature black liquor process from the bar gasification process. This will allow further research work to be done on this technology. I redo this one because considering all these issues, we decided to make some more changes to the global process. Due to the complexity and the low impact of the current black liquor gasification process compared to the whole plant, we decided to separate the non-mature black liquor process from the bar gasification process. This will allow further research work to be done on this technology on an industrial case and will allow it to be reattached to the rest of the plant when the technology has matured. The bar gasification process is quite mature itself. Therefore, we will be able to produce syngas, which can then be converted to syncrude, and the syncrude will be directly sent to the refineries instead of constructing a dedicated distillation unit, while the gaseous products of the Fischer Tropsch reaction will be purified to remove the inert gases before being recycled in the dry gasification reactor. The most important thing to understand is that in order to optimize a plant's design, one has to take time to rethink the global process in order to avoid low impact units, which will require investment for limited results. Every possibility should be considered to avoid complex units or to group different units in a single one. The resulting simplifications lower the construction and operational costs and make the plant more competitive. Thank you for your attention.